Hi everybody, and thank you for listening to this oral presentation that is about arsenic adsorption using immobilized magnetic iron oxide nanoparticles in electrospun PVA. My name is Nicolás Torazo, and this work has been carried out by a research group in University of Buenos Aires, together with colleagues from the National Atomic Energy Commission, and also from the Materials Physics Center in the Basque Country of Spain. Argentina is located in the southernmost tip of America, as you can see, and it is one of the many countries affected by arsenic presence in water. In fact, contaminated water has been reported throughout its geography. It is estimated that more than 4 million people is exposed, roughly an 8% of the population. There are many ways to remove arsenic from water, like the one shown in the picture, reverse osmosis, coagulation flocculation, etc. In particular, adsorption is promising because of its high efficiency and reversibility. Iron oxides, like magnetite, are well-known arsenic adsorbents. Taking into account that adsorption is a surface phenomenon, a great way to increase the active surface of a material is by reducing its size. Nanometric magnetite is easy to synthesize by coprecipitation of ferric and ferrous salts in the presence of basic media, and adsorption on its surface occurs mainly by ligand exchange, in which arsenate species form inner sphere complexes with a crystal structure. A slight acidic media favors this reaction. The main problem of using nanoadsorbents is their potential release to the environment and the clogging of filtration columns as a result of particles agglomeration. But what if one could immobilize the nanoparticles in a permeable membrane? This is where electrospinning comes in. It is a technology to produce polymeric nanofibers, in which a polymeric solution is injected through a needle nozzle pointing at a rotating drum collector. When the nozzle is connected to high voltage, the solution charges and the electric field pushes the solution towards the grounded collector, like can be seen in this picture. During the flight, the solvent evaporates and solid nanofibers are deposited. This is an emergent industrial technology, as it gained special attention for the fabrication of air filtration devices like masks for the COVID-19 pandemic. Specific adsorbents can be loaded in the electrospinning solution. So in our work, we've loaded nano-magnetite in PVA nanofibers in order to produce membrane-like arsenic adsorbents. We chose PVA because it's a water-soluble polymer that swells underwater, like can be seen in these AFM images. And moreover, it is already known as a magnetite stabilizer, and it is biodegradable. We prepare electrospinning solutions using two approaches. In the first approach, we suspended previously synthesized and dried nanoparticles in a PVA solution using a tip probe sonicator. Final nanoparticles concentration achieved was 0.1% with respect to PVA. The results obtained by these methods were published last year. In a second approach, precursor salts are dissolved in the PVA matrix solution, and then sodium hydroxide is added to precipitate the nanoparticles. This is a one-step method that produces a long-term stable suspension. There is no chemical waste. It's easier to scale up, and it allows a higher concentration in the solution. We have preliminary results for this, and there is 1% using 1% with respect to PVA. So then we electrospin the solution and perform a heat treatment of the membranes at 190 degrees Celsius and 10 minutes to insolubilize the membrane. So what did we obtain? A membrane like the one shown here. Some images reveal the nanofiber composition of the membrane with diameters ranging from 100 to 150 nanometers approximately. This membrane has an estimated specific surface area of 23 to 33 meters square per gram. Now, transmission electron microscopy revealed the nanoparticles lying inside the nanofibers. They are excellently dispersed and they have a size of approximately 9 nanometers. Further studies were performed to analyze the composition of the membrane. The magnetic behavior was confirmed by vibrating sample magnetometer with saturation magnetization of magnetite giving 74 mu per gram, and X-ray diffraction showed the inverse spinel crystal structure within the fibers, corresponding to a magnetite. With this material, we performed batch adsorption experiments. Isotherm of adsorption shows the typical linear behavior for low equilibrium concentrations, and saturation of the adsorbent was not reached in the studied range, corresponding to typical arsenic concentrations in contaminated water. We conclude that the maximum adsorption capacity of the nanoparticles was at least 52 milligrams of arsenic per gram of magnetite. An interesting behavior was observed in kinetic experiments where we can see a delay before actual adsorption begins. This can be explained by the swelling of the membrane. Here, we show a schematic representation of the adsorption mechanism proposed by us. Red and blue dots represent arsenic and water. During the first hour, the nanofibers increase their diameter and solution flows inward, not altering the solution arsenic concentration. Once the fibers are wet, diffusion of arsenic begins in the inside of the nanofibers, and it can be absorbed by the nano-magnetite within. These results were published last year in Journal of Environmental Chemical Engineering. What about in situ synthesis? Here we show preliminary results obtained for the in situ synthesis approach. We can see a greater amount of nanoparticles inside the PVA matrix and a possible salt crystal growth. There is an excellent distribution along the fibers, and this is an important issue because agglomeration would reduce active sites on the magnetite surface. Adsorption isotherm showed excellent results. We could lower the arsenic concentration of water from 100 microgram per liter to less than 1 microgram per liter with an absorbent dose of only 30 milligrams per liter of magnetite. Moreover, we performed a cost estimation which indicate that less than $0.8 can produce enough material to clean 8 tons of 10 micrograms per liter contaminated water. So we conclude that this method allows an excellent dispersion of nanoadsorbents inside PVA nanofibers. In turn, this favors the high efficiency observed in adsorption experiments, reaching less than 10 micrograms per liter with initial concentrations of up to 500 micrograms per liter. And in situ synthesis surpasses suspension with tip sonication in terms of magnetite content and solution stability. We will study the kinetic of adsorption for the in situ approach, test higher nanoparticle concentrations in the matrix, test reuse of the membranes, and performance in real waters. This work was supported by our institutions, is currently funded by an ECOP project funding in Spain and a national funding from the Science Ministry. I thank you for your attention and look forward to meeting you at the conference.